Hello, 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 Isabella. Hello, hello. Good afternoon, Isabella. Wait, okay, I'm gonna do it this way. Hello, Melissa. Good afternoon, Isabella. Hello, Amanda. Hello, Rachel. Hello, Lydia. What else we got? Hello, 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 Farina. Here it comes. Hello, good afternoon, Farina. Awesome. Okay, here comes. Okay. Okay, Amanda, did I say Amanda? And Billy, hello, good morning, good afternoon. Leslie, did I say hello? Okay, hello, Leslie. I think that's everybody. Okay, I think that's everybody for now. Hello, hello. Okay, I think we can get roll. Like you guys are rocking on homework. I think you are where you're supposed to be. I mean, I think there are like, I will say this. I think there are like, I can even go through right now. There are like 3 outstanding on homework 1 and maybe 3 or so outstanding on homework 2. Doors not closed on them. I'm on homework 1. I might not give you a full 50 points, but please, please, please do get them in. Like, please do not think that it's too late or something like that, or that it would be stupid for you to do it. It wouldn't be. There aren't that many homeworks, right? Like you can catch up, blah, blah, blah. Um, but everybody who has it, but if you've handed in 2, you're totally solid. If you've handed in 3, that's awesome. And you're not getting a new one for a little while. So if you've handed in 3, you're breathing for a bit, for like a day. Like there's nothing due till Wednesday, and we're going to talk about 3, blah, blah, blah. But also, we'll talk Wednesday about exam. Like I know I had originally said something about exams and we haven't talked about it in a while. If we have to adjust the date, we will. Nothing's going to sneak up on you. We're not having an exam until I give you a review, practice, exam, blah, blah. But we'll address all that this Wednesday. Like today, I'll take any questions about anything at all. But if it's about any potential exam or concern exam, let's just keep that for Wednesday, just because I think we have a little momentum now and I want to keep it going. So anyway, I think you guys are all on top of homework. I think that if you did turn in anything at all until like, wait, if you've turned in something today, then I haven't seen it yet and balls in my court. But if you turned in anything at all up until like last night, I think I'm caught up. So you should have gotten anything or everything back. If you've turned in something and it's not back, you might want to alert me or something. Again, also on any homework that you've turned in, like no matter how long ago it was supposedly due, on any homework, if you got less than a 50, it's still always possible for you to get a 50. Like I try to be explicit about that in the comments, but even if I don't tell you explicitly, like if you got less than a 50, that means there's something you could do if you care to resubmit and then get the full 50. Even if it's not totally clear, if you have a guess, take the guess. There's no way you're going to make your grade lower. I'll tell you that. As we get further, it might not be worth it to do that. Like, you know, if you're getting any points at all, it might not be worth it. But right now, if you have anything less than 50, don't take it as a criticism. Take it as a, you could still fix it if you want, if you can. But yeah, you do want to get 1 and 2 in. But so I'll take any question about anything, but if it's about exam, let's wait on that till Wednesday, like even if it's about when is it or something, because we won't fully have that sure until Wednesday. Okay, that said, I feel like, was there any other announcement or anything? No. So I'm going to start just getting right back to where we were in the material, which was, in my opinion, as far as I know, we were going over homework 2, math methods. We were in the middle of it. We were on letter I of part 1, I think. So that's what I'm about to go back to. And we're just going to go through it and talk, and I have things to say. So, but if there's any questions at all about anything at all, totally stop me now or stop me at any time. Like I'd rather answer questions than lecture. Like it's not an interruption. The lecture or the going over homework is just like where the train goes if someone doesn't give it a better station to go, kind of thing. So I'm shifting gears to the board. Pardon me for a second. Right. Okay, yes, this is where we are. So hang on 1 more second. Blah, blah, blah. Okay, all right. So where were we? I'm sorry, that's not what I meant to do. Right, where we were, I think. Now stop me if this is wrong, or if it's a good place to, if you just want to throw something in the chat like that, it's right. Where I think we were was we were in homework 2, math methods. We were in part 1. Okay, we were in letter I of part. Oh, sorry. We were in letter I of part 1. Letter I of part 1, and all and we may have done it already. I'm sort of backtracking just to refresh us, but like all of a sudden, the question of part one is seemingly out of nowhere. It's like, hey, by the way, is x equals e to the negative omega t a solution to our standard differential equation? I'm actually going to write this exact same thing again. I know this is all sloppy and already written on, but right out of nowhere, that's the question I. Now we've been practicing trying solutions and seeing. We've been practicing trying potential solutions, equations that are potential solutions to our one favorite differential equation. What we've been trying to do, in other words, is see different mathematical ways to describe what we know to be the harmonic oscillator. Now, and we've gotten used to the idea that cosine is a good way to solve that differential equation. Cosine is a good way to describe a physical oscillator. Now we're suddenly asking, here in the math homework, we're suddenly asking, hey, cosine, yeah, fine. Cosine works. Even cosine with like a phi extra constant, we found out it works. Yeah, cosine, and it works because like, well, it works. Well, why does it work, we think? Well, one of the reasons it works is cosine, like oscillatory behavior, back and forth in time. Oh, back and forth. Okay, the cosine graph. Yeah, it seems to shape-wise make sense. But also, why are cosines the way to describe harmonic oscillators? Well, also because this differential equation, which I'm going to write again in 1 second, I'm going to write it right now because oh, pardon. Sorry. Okay, great. This is the question. Again, this is a question of part I of part one of the homework. Like it's coming up in the homework, but it's also a very real question. Like we're suddenly shifting, like this thing here is the mathematical way to write Hooke's law. This thing means oscillator, right? And we've been picturing oscillators with cosine functions. Now we're suddenly asking, hey, could we use E like an exponential function or exponential function? Because that's what they always look like, right? They're always like, or they're like, Can we use an exponential function to describe an oscillator? That's what this is asking. I mean, yeah, it's asking. Okay, the real physical question that's being asked here is, I mean, it involves math, but it's a physical question, which is, can we somehow, if we're trying to predict what an oscillator is doing, which is our whole subject in class right now, like for good and for bad, like it might be really boring, but that means you're really getting comfortable with it. All we're dealing with in class right now is the physics of the space-time predictions of an oscillator, right? Like mass on a spring or Bob on a pendulum, but any system like this is what we're all about in this class right now. And what we've been saying is cosine functions are a direct way to describe and predict the behavior or something like this. Now we're asking, what about exponential functions? Okay, we're asking, could we use an exponential function to satisfy this differential equation, this description of an oscillator, right? We're asking, can we use exponential functions? Now, exponential functions that doesn't mean power functions. I don't mean like y equals x squared or y equals x cubed. I don't mean like a parabola or cubic. Those are power functions. I mean exponential, like y equals e to the x, or like 2 to the x, or 3 to the something to the x, not x to the something, right? I'm talking about exponent, and in the world, in New York, in the newspapers and on TV, people frequently will say something is exponential when they just mean it's power. They just mean it's big, basically. Exponential, remember, means like e to the, which means the kind of thing that's come up in your math classes whenever you're talking about radioactive decay or population growth or interest bearing and savings accounts, like whatever those examples are, like in math, like, and I'm going to talk about, but we're talking about that kind of function, an exponential function, as in growth or decay. And we're asking now, can we use those functions to describe an oscillator? Now, on the one hand, like, that's a weird question. Why would we possibly describe something that goes like this with a graph that goes like this? I'll tell you why. The reason why, and maybe it won't work because maybe it is weird, but the reason we're even trying this at all is because E has the kind of property that cosine has, which is called a feedback property, or which is this. Cosine, when you take the derivative of it, you get someone coming in the room. Excuse me, sorry. Okay, cosine. Take the derivative of it once, you get negative sine. Take the derivative again, you get negative cosine, right? So take two derivatives of cosine, you get back to cosine, but multiply by a constant, by a negative constant, which is exactly what this equation says, right? The equation is asking us to look for, and I know I've said this a million times, but please, like, I can't say it enough. Like, this equation is asking us for something which, when you differentiate it twice, you get back to itself, but times a negative sign times a constant. Well, cosine does that mathematically, right? Like, we're going to stop and think for in a minute what it even means that it does that, but it does that. That's one of the reasons it works. That is the reason it works. But E also does that. You take the derivative of E once, you get E. I mean, what if you have e to the y equals e to the x, dy dx equals e to the x. Do it again, you get e to the x again. Now, there's no negative sign there. There's no negative sign there. So something might not be totally right. But there's something nice, which is that you get back itself, like with cosine. So there's something about the exponential function that's like the cosine function, neither of which is like a power function. Like, no power function is like this, right? Like y equals x squared, y equals x cubed, y equals 1/2 at squared. But all of those, if you take enough derivatives, you get smaller, you get simpler and simpler functions until you get down to zero. Well, until you get to constant functions, and then you get to zero. I don't know if I'm saying that too fast, but right, like y equals 1/2 at squared plus v naught t. The derivative of that is y equals at. The derivative of that is y equals a, right? Like, and eventually the derivative of that is zero. It bottoms out. Cosine, nuh-uh. And E, nuh-uh. You keep getting derivatives. So E has an attractive mathematical quality that says to us, can we investigate it and see if somehow we can use this function to capture harmonic oscillation in physics? Okay, so we're going to try it. That's where it's coming up. That's where we're going to try it now. But we're going in knowing there's something a little weird. Like, first of all, exponential functions are like monotonic. They like go up in a direction or they go down a direction, but they don't wiggle back and forth. So they're weird. Also, there's like a negative sign issue. Like, there's no like derivative of cosine, you get negative sign. You get that negative sign. And then it stays there when you do the derivative again. But e to the x, you get e to the x. You don't get it. So there might be an issue. So we're going to find out. Like, this is why this is like experimentation or scientific thinking or whatever. In this problem in I, they're asking us, could this work as a solution? Well, everything I just said was just conjecture as to why I would even care. But we can always just try whatever we have. So I'm going to do it right now. In fact, I'm going to pause because I've been talking so much. I'm going to say, like, what we're looking for here. I'll put on the next page. What we're looking for in order to check, if you're still like with me, we're going to check like the conjecture. The conjecture is that x equals e to the, I forget if we put a negative, did we put the negative? Yeah, so we put a negative sign there because we were like figuring we need one. E, right? The question that we're checking is, does this satisfy, or in other words, solve the original differential equation that we always have, whether it's written with x's or z's or whatever, this differential equation, which is not the only differential equation in the world by any means, but it's the one that means simple harmonic oscillation, right? So it's the physics one that we care about right now. This is our question. So what we're about to do right now, many of you, most of you have like already done this for homework and you already turned it in and got it back. So this won't be hard. But whether you did it or not, what we're up to now is this point where you actually get the first derivative and then you get the second derivative to see what's what. It's practice, it's exercise, whatever. But I'm going to pause and say, I'm not going to go any further until I get a bunch of people answering this either in the chat. You could do it privately, you could put it publicly, and I'm not going to say whether people are right or wrong, but I'm going to be like, yay, thank you. And you could totally put it in for the points. And the point thing really is working, by the way. I got to say, those of you who are keeping up with the point thing, you're getting like a lot of points. And those of you who are not, are not. So like margins are widening just by the class participation points. So like do them, please. Like I think it really, anyway. So I'm going to pause and say, it's not a competition, it's not a race. I'm going to wait. But anybody who knows where I am or can catch up and come back from the bathroom now, just like do this first derivative, do the second. It is what you did in homework for part J, but whether you did it or not, or did it correctly, just now, you could put the answers in the chat, in the private chat, you could say them. I won't say if they're right or wrong. So if someone already put it in, you could still put it in. So I'm going to shut up. I want everybody, or anybody who wants some points, to please do this. Get dx dt and get d2x dt squared for this conjecture. Like this is what we're trying, and we're trying it because we're learning math that we need, but also because of all the reasons I just said. We're trying it because it seems like it might possibly be a way to describe harmonic oscillators. So that's the question. So I'm pausing. Oh. Now notice, at the risk of embarrassing him, I'm saying go Farina, meaning yay, Farina put in an answer. Thank you, Farina. Totally acknowledge. Way to go. And she can, by the way, submit this not only for the 50 points of participation, but for the like 4 right or wrong portal, because she just took a risk and said something that might be right or wrong. But by the way, I'm not saying she's right. I'm just saying go Farina, like yay. But anybody else can still put it in because I'm not saying it's right or wrong. So you don't know. So you're not copying her because blah, 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 blah. But yay, go Farina, yes. And similarly, go Isabella. Same point I'm making. You see my point, right? Okay. And this is, again, not to embarrass any or to blah, 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 anybody. It's to blah, 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 you know, blah, 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 something, something. Oh, go Rachel. You know what I'm saying? I'm saying go Rachel. You know what I'm saying, people? All right. So keep it coming. Like make, so all of you, the task. So it's not a competition. Just make sure you get this. The more you can just take derivatives like piano scales, the more you can like do the chords and blah, blah, metaphor or something. Did I say go Rachel? Yeah, okay. So who else? And again, I'm not saying that these people, and they can do the second derivative now, the people that, and I'm going to go over it in a second, but let's get everybody, make like, whoever wants to blah, blah. And it can be a private chat. You can do private. I don't, or I mean, excuse me, a direct message. Um, oh, oh, hey, speaking of which, I just saw two that I missed. Are we taking the antiderivative? No, we're actually, right. No, okay. Oh, right. So good. Well, good question in the direct message. Like with the task at hand, and I know I missed it. Like a question was asked like 3 minutes ago, but I think it's still relevant. Like it would seem, oh, this is a really good question. I'm just going to read it. I'm not going to say who it is, but I'm just going to read the question out loud. The question says, so we are taking the antiderivative of negative omega squared x. Okay, that's what the question says. And let me say again, I'm going to say that the answer is no, but this is a great question. The fact that the answer is no does means still that it's a great question. She's asking like, see, look at this. So I'm asking everybody to solve this. This is the question, right? But what's weird about this, what's unusual about this type of math or science is you're used to people say, I'm asking you a question, what's the answer? Here, what we're really doing is it's kind of multiple choice. In a way, we're saying, here's the question, and I'm asking you true or false, does this answer work? Okay, like is this thing, this thing, an answer yes or no to this question? Like that's what's going on, right? But the question is, can you find a function? The question here is, find a function for which when you differentiate it twice, you get back itself times a constant times a negative. So somebody in the direct chat is very reasonably saying, okay, so are you asking me to do two derivatives backwards? Because like in a way, that is what I'm doing. I'm saying, I want you to think of a function whose second derivative is blah, 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 blah. So what's the function? So the person in direct chat is very rightfully going, okay, you're not asking me to take two more derivatives. You're saying that the function already like got differentiated twice, but you're looking for the function. So are you asking me to anti-differentiate backwards? Okay, yes, in principle, a differential equation, if anything, is asking you to antiderivative, right? It certainly is not asking you to differentiate. It is asking you to go backwards, but what we were trying to prove in the first week of this class, and this is to everybody, this is why this takes so long, okay? What we were doing in the earlier exercises, or like 2 weeks ago, is we were trying to show that why this thing you can't, yes, that's what it's asking for. It's asking for us to go backwards with derivatives, but you can't literally just do that. If by anti-differentiate, we mean integrate, because that's what we kind of think we learned in math, that like, oh, the antiderivative is the integral. If what we cannot do here is just integrate twice. It seems like we could if this x were a t. That's what I was trying to show 2 weeks ago. And then again, I'm not yelling at it. I'm excited that someone's asking this question because no one ever gets this until they do for themselves. You know what I mean? Each one of you will get this at your own moment. Some of you already did. I don't know. And some of you will. But it's not just because I'll like say it once that you're going to get it. Like I'm saying, if this thing were a t, then we would just anti-differentiate this backwards. But this thing's an x, so we can't. We have to sort of we have to like take a guess and then check it. So we guess that okay, good, thank you. Okay, cool. But I think this is good. So we guessed this e function here that I'm making a mess out of at the top. And now we're going to differentiate our guess twice. We're going to differentiate our guess twice to see if it works with the equation, because that's the only thing we can do. And that's why I'm going to take two derivatives now. We're literally going to take derivatives and see if when we do, they do the thing that they're supposed to. Yeah, all right. So I'm going to do that. I still even want to say more about this. It's a really good, did I say it was a good question? It's a good question. Totally put in the little, okay. So but now I'm making such a mess, hopefully you guys still remember the function. So if I take the first derivative, actually here. Okay, that's nice. Oh, the wonders of like, whoa, it never happened. See, it never happened. This is like some former presidents of the United States like got divorced when their marriage didn't work out. But John F. Kennedy, you thought you knew where I was going with this, but you didn't. But John F. Kennedy, I see that. Oh, very good in the chat. Yes, I'm going to keep talking, but yes, good. John F. Kennedy got not John F. Kennedy. I mean, his wife. Oh my God. how could I forget her name? Wait a second. What is Kennedy? Wait, this has nothing to do with anything, but I cannot believe I cannot. Jacqueline Kennedy. She didn't get divorced. She got an annulment. Think about that. Like, not like the marriage is over, we get to start again with a different marriage with a different person. No, annulled. Like, it never happened. Like, that's deep. Like, that you really got to be someone to get that. All right, so that's what we're doing here. We're annulling this. Sorry, we're like annulling this writing, and so I'm saying the first derivative of x equals e to the negative k. So this is what a lot of you put in the chat. To go all the way back. Thank you for putting in the chat. And yes, I agree with you. You do chain rule and the E rule, so you get dx dt equals negative omega e negative omega t. Okay, right? Like many of you said, like almost all of you said, thank you. And then if you do that derivative again, you bring down the negative omega again, chain rule again. So you get omega times omega, okay, omega squared, but the negatives come down, right? So two negatives make up, so you get positive omega squared e to the negative t omega t. Okay, so what does that mean? So then you go, oh, well, wait a second, like that's cool, like looking familiar. Oh, good, I see that I got back. Oh, yes, just like I hoped, I get back my original x. So that's that good quality. What I'm ultimately in a minute going to call the feedback quality here, that even the rate of change gives back the original function. Okay, so that whole thing was what we were checking to be x. But what does this mean then? This means thus, if right, just to be as oh, let me look in the chat. Hold on a second. But I think this is the answer. Chat. One sec. Oh, wow, you guys need, thank you. Oh, the Kennedy thing. Yes, I'm sure you said that faster than I thought of it. I didn't see it, but thank you. Yes, Jackie, awesome. That's, you totally get points for that. You can, and you get points for knowing that. You should know that stuff. That's great. There was another funny thing about that. You know, the other thing that, well, anyway, but so now here on the math, here's my point now here. I mean, this is actually like is stuff like this is partly this is practice with these different derivatives and differential equations, and like even if just secretly you're starting to understand derivatives better, then great, right? But we're also actually what we're trying to do here is make predictions about oscillators. Like that's still the physics program. That's why we're monkeying around with all this math. And what we've just shown ourselves is, we were right to suspect an exponential function because it has that quality that we're looking for. But we also were right to wonder, is it good enough, the exponential function? First of all, there's something wrong with its shape. But second, more important, it doesn't seem to do the thing to the negative sign that we seem to need. So this doesn't work. The exponential solution does not describe the oscillator as is. For the whole reason, the entire reason, and this is how technical all this is now, like this is how precise we have to be, is just because that negative sign didn't work, the whole thing doesn't work. Like meaning, not like meaning this, like this blue, this thing right here, the plot, okay, that is a differential equation. I'm not saying there's anything wrong with that statement. Like that's not an error. That is the second derivative of x with respect to t, and it is a differential equation. It just isn't the one that we wanted to solve. It's a different one. It means something in math. Frankly, it even does mean something in physics, but it doesn't mean this thing that we're interested in. It's not the simple harmonic oscillator. Simply because of that negative sign? Yeah, because the negative sign was there originally, is still there from Hooke's law. The negative sign is the physics deal. It's saying it's a restoring force. If the mass is over there, the spring is pulling to here. If the mass is over here, then the spring is pulling to there, right? That's what that negative, that's how you get the oscillation, that your derivative is always running in the opposite direction from your function. Like the negative sign really is key to the oscillation. And if we don't get the negative sign, we get something, but it's not oscillation. Okay, so the exponential function as is does not work for the reason we suspected. Okay, I'm going to go. But what we might quickly do, one might quickly say, okay, wait, but maybe the reason the negative sign didn't work is because like a negative times a negative is a positive, and we stuck that negative sign in this right here. We stuck it in the right here. So didn't we make it? Maybe we made it harder on ourselves from the beginning. Like if the negative sign's the issue, can we just like try without that negative? Is that? And I'm going to say yes. Like it's not in the homework. So we are in the homework right now. We're in part 1, part I, like part 1, subpart I, and they both look the same because they're both capital. I'm sorry. Before we go on to J, I'm just going to add a page here. Before we go on to J, just to make sure that you see that this is all part of a program. None of these are just none of these thus far is just a random exercise, even though they are exercises. We're saying, okay, sub part I continue. Oh, sorry. Oh, excuse me. Oh, hang on a second. I have to get somebody a glass of milk. I'll be right back. But what I'm about to do, everybody should try, and if you put in the chat, it's more points. Try, and I'm about to do this fast, but now I'm going to run away for a second. So try x equals e to the positive omega t. Just check and make sure whether that works. Like maybe our negative sign is because all that didn't work was a negative sign. So get rid of the negative sign and see if that works or not. But I'll be right back. I apologize. Hold on. We're still on the same question. I'm looking at the chat. So the question is, well, okay, and well, I'm just going to do this quickly. So, again, if you want to put it in the chat. So let me ask you guys, does x equal e to the positive omega t work, yes or no, according to this? Like, this is the question I'm asking now. Like we just did this. It was a sidebar from from part. Thank you. Exactly. Well done. And I'll leave it at Amanda. Yes. Way to go. Yes. And yet she's correct. And I'll leave it at right. It doesn't work because, again, we don't have a negative sign here, right? That's awesome. Okay. So whether we make it a negative sign or a positive sign, this exponential solution does not describe simple harmonic oscillation, is what we're saying here. Okay, that's what we're saying. And we're also saying that's just progress through the homework. And if there aren't questions, then I'm going to go on to J. But now something funny happens in J. Now remember again, why did I try the exponential in the first place? Because it has that self-referential quality that the rate of change of the function yields the function itself. That's why I tried it. But why didn't it work? Because of negative signs, right? So now all of a sudden I try this other weird thing as a mathematician, or I try the next, I go to part J of the homework again. So part. And I believe in this one, and correct me if I'm, but now in this one, it says, well, yeah, I don't know if it uses the word assume or conjecture or given, or you can tell me, but we're now suddenly conjecturing, what if X, yes, we're conjecturing that X might equal EI times omega t, where I is a shorthand for the square root of -1. Now that's a leap, right? Like, whoa, suddenly we really are in a math class, like imaginary numbers now. And like, frankly, even if this were a math class, that if I were in this math class as a student, and all of a sudden I was sitting there on the page, I'd be like, I didn't know that was part of this class. Like, I might even be interested depending on but I would certainly be like, well, where'd that come from? And now this is a physics class. So where the heck is I all of a sudden? Well, I'll tell you where it's coming from. Where it's coming from is we got this negative sign problem. We've got this situation where like we feel like E is a function that might describe something of what we're doing, but we need to generate a negative sign. And the thing is, what we're doing is taking two derivatives. So we're doing something twice, like we're using chain rule, we're bringing down an omega right twice. And the thing is, what we're hitting this wall where like a positive times a positive doesn't generate a negative sign. And a negative times a negative makes the negative sign go away and generates a positive, right? And we're getting positive either way because we're squaring something. And we want the thing that we're squaring to end up yielding a negative. But we can't get there because remember, well, I don't know if you should write this down, but remember, a positive times a positive is a positive, and a negative times a negative is a positive. So if you're looking for a number that multiplied by itself gets you a negative, like it doesn't seem like there's any options. With exactly the problem that we're having right here with chain rule. But in math land, that whole idea we give a name to, like whatever would be the number that multiplied by itself would be -1, we call that I. You could say it's imaginary. I don't know if that helps you. I'd rather call it complex because it does seem like a complex idea to me. You could say it's imaginary, but like I say to you, is the square root of 2 not? I mean, it's all in our imagination, I think, or it's none of it's in our imagination, but it's not really an imaginary number. It's just a letter for a concept for a number that we don't see on the number line. Like it's not to the left of 0. It's not to the right of 0. It's somewhere else. It's in the complex plane of numbers, apparently. But whatever this thing is, do you have to have taken a math class on it? No. I'm just saying now, from here on in, whatever number, when you square it, gives you -1, we're going to call that I from now on. And we're going to introduce it right here because it is meant to address exactly that weirdness of like when you're like, I need something that multiplied by itself gives me a negative. Oh, I can't do a positive because that will make a positive. I can't do a negative because that'll make a positive, right? That's exactly the issue we have here with the omegas, that they were almost there except for that negative sign. So we just decided to try. What if x equals e to the I omega t, right? Then I could stop and ask everybody, but I think I'm not going to. Then we find, feel free to put in the chat if you want for love or money or whatever. When someone's here. Okay. Oh, and I'm sorry. So do you need to know anything else about imaginary numbers besides just exactly this statement? No, you don't. Oh, excuse me. Sorry. No, you don't. But whatever square roots mean, everything follows. But you need to know one other thing. Sorry, and I am going to pause and ask you all to do this because actually I am going to ask you to pause. And no, I'm going to pause and ask you all to do this and put in the chat and whatever. But you're just going to follow the normal rules of derivatives like you did in the homework. But just the only other special thing you need to know about I is that it's not that special. It's just a number that will remain the same throughout any given problem. So it's a constant, right? Like, so when it comes to derivatives and stuff, it's not ix, it's just I. So it's a constant number. So you treat it that way. So I'm going to ask you to do these two derivatives. Okay, you've probably already done them, but please do them with the I in there now. And also, I'm going to pause for a second. So please put in the chat whatever, but something just happened I have to address. Okay, sorry. Okay. Should I be worried? Does anybody want to put in the chat the, or can I get a, or, oh, okay, thank you. Oh, wow. All right, Isabel. That was, wow. All right. And I'm going to say on that note, especially, wait, just making sure here. Yeah. So I'm going to say yay, Isabella, for doing that. But also, she's totally right. We don't even have to go further. That's great. And it makes a point. Okay. So yay, and thank you. And I'm not going crazy. And I'll spell it out here. Obviously, it's hard to read. Like, even if you do understand what she's doing or whatever, it's like hard to read these things in the chat, of course, with exponents and stuff. So just to be clear, what she says, she's doing chain rule and exponent. But she's just treating like a constant, like just some number like 4 or b or whatever. So she's saying the first derivative is like this. And then she's saying the second derivative, chain rule again. So the I comes down again and the omega comes down again. So she gets like this, right? Like, and correct me if I'm, but she says this, but then she says in that brain, she goes, oh, I may not know everything in the world about complex numbers, but I know if the one thing I need to know is that I is defined to be the square root of -1. Therefore, if you square it, you got to get -1, right? So that's why she's saying, oh, I mean, she's not saying, oh, I'm saying, oh, but she said, but to be as clear as mud, I'm saying that if we put together this weirdo thing of like we have oscillator, right? Back to physics. We got something going like this. Or now we've like something like this, if you're thinking of it as X. Once you kind of do lab number 2, and you see that the pendulum works the same way, and you look at the math from lecture and you're like, you can change the X's to Z's, realizing that Z could stand for an X or a theta or anything. You're starting to realize, okay, we're talking about systems that are going back and forth in some kind of way. Maybe it's the color that's going like red, orange, yellow, green, blue, indigo, violet, indigo, blue, green, yellow, orange, red, right? Like, or it could be temperatures like homework 3. What we're trying to say is we're here as physicists, we're looking at systems that are going back and forth in some kind of way, where some measurement in time is going back and forth, back and forth. Now, the cosine is the most obvious way to describe that. But we pause for a second and say it's obvious not obvious, but it's the most direct way to describe that. But then we say, but maybe exponentials will work because exponentials have that quality that cosines have of like the derivative of the thing is the thing, right? But then we go, oh yeah, but they don't work with the negative signs as well. Then we bring in this I character to solve our negative signs problem, and lo and behold, it works. And what does that mean? It works. It means that evidently, if we are willing to use complex numbers, imaginary numbers, then if we're willing to use them, then we can like put them together with exponentials in order to describe what cosines already describe. Like apparently oscillatory behavior can be described with some complex, literally complex version of exponentials. Why would that be? Like, that's bizarre. Like, that either says something weird about math or it says something weird about physics, that we could put together imaginary numbers with exponential functions in order to get oscillatory behavior. Like, what is, and why would it be worth me talking to you guys about? I mean, if it is just an abstract, weird math coincidence, well, first of all, there's no such thing as a coincidence in math or science. But second of all, because there is a reason. Because, well, oh wait, are people, well, yeah, I guess. Okay, I'm going to go on. Like, what do I mean by the reason? Or like, what I'm saying this. Oh yeah. All right. First of all, like, okay, so my question right here, and do please write this down. I'm saying again, as a physicist, I'm saying why would exponential functions like monotonic, like again, I'm in the back of my mind. Look, I know the rest of the world definitely does not understand exponential functions. They're always saying on the news, like, and it's going to exponentially, the virus will exponentially, the vaccines will exponentially, blah, blah, blah. Okay, most of the time that people are saying exponential there, they really just mean something really big or really small or something that's fast rising or fat. But what exponential really does mean something. And I know we might, but whatever it means, it's whatever is in your mind to be associated with like decay or growth. Like exponentials go up forever or they go down forever. They go in one direction forever. And you'll see that again in a second. The question here is why, when you take a function like that, would you be able to describe something that goes back and forth like this, as long as you introduce complex numbers? Like, what kind of nonsense is that? Well, the characteristic that is similar, the underlying shared characteristic between complex numbers, exponential complex functions, exponential functions, and trigonometric functions is something called feedback. What we're talking about here really is feedback. Feedback is the quality of, you might say, self-reference. Like the most obvious form of, not, I shouldn't say obvious, the most common form, like when you say the word feedback, the first thing that most people think of is that auditory feedback thing, like that screech, horrible sound that you hear when the microphone gets too close to the speaker, right? Like that feedback, like what it, now that's a horrible, unpleasant, but very, very accurate, very demonstrative version of exactly what feedback is. Like that's an unpleasant version, but it's a very, very good example of feedback, in the sense that what's going on there is that sound is coming out of a speaker and going into a microphone, which is coming out of a speaker and into a microphone. Cause is leading to effect, which is leading to effect, which is leading to effect. Like there's a cause, if there's a chain reaction going on there, and the volume builds up to the point where it goes off to infinity, and infinity means unpleasantness. More specifically, feedback, it, okay, remember, this whole, all of this stuff, this all goes back to the question I think was asked today by someone in this room. Yeah, this all goes back to the thing of like, if the right side of what was going on was a t, we wouldn't have all of this weird math, all of these discussions. We would have a second derivative and we would unwind it by doing backwards derivatives twice, integrals, right? But that's not what we have. We have a situation here where the rate of change of effect with respect to cause is dependent on effect, not cause. If this x were a t, then effect, we would be saying, in short, that the rate of change of effect with respect to cause depends on cause. And that's like the way cause effect works. Effect depends on cause. Cause leads to effect. But this thing is saying, remember, x is the dependent variable, t is the independent variable. Just by the way this is written, I know that. So the clock is ticking and the mass is somewhere at any given moment in time. And what this thing is saying, this is literally an example of feedback. This is self-reference in the fact that this thing is saying the rate of change and the rate of change of position with respect to time is a function of position. Like, that's weird. I'm saying it over and over in the hopes that eventually it will confuse each and every one of you for a moment. Like if you're never confused by this, you're not looking at it closely enough. Something confusing is happening. I mean, what we're saying, like this, we're saying the rate of change of position is with respect to time is a function of position. Let me put that in more clear English. What this thing is saying, this Hooke's law, differential equation, oscillation, it's saying, like, okay, I'm a physicist. I want to know at any given moment in time, where is this mass? So I go up to this equation and say, can you tell me where the mass is at any given moment in time? That's what we always want to know in physics. Like it used to be like x equals 1f a t squared. Can you give me a xt relation here? Can you tell me where the mass is at any time? And what this equation says is, oh yeah, I could tell you that. Just do your good old physics. Remember your good old physics. You just, as long as you know the acceleration, as long as you tell me the acceleration at any moment, then I'll tell you where the thing is. Remember from physics, like that, you know, acceleration is really important, the equation said. So as long as you know the acceleration, you can know the position. So then I say, okay, so you need to know the acceleration in order to know position. Fine, fine, fine. So how do I know the acceleration? And the answer is position, right? If I want to know what this is saying, like this is saying A depends on X, but X depends on A. That's what this is saying. It's saying, but X depends on A. Like in physics, X always depends on A. In physics, you always need to know the acceleration to know where something is at any given moment. But this thing says, well, what the acceleration is, it's not a constant anymore. It's changing all the time. Oh, so it's changing as a function of position. So if you want to know position, it depends on acceleration. If you want to know acceleration, well, it depends on position. That's what it's saying. That's what I mean by feedback. Like that's a weird thing. It's actually amazing that we could even solve a thing like that at all. Like it seems like it shouldn't even be solvable. Let me give you 3 more examples of that super fast, just to remind you from math class, right? Like you like interest bearing savings account. Like don't be intimidated and don't worry about the numbers, but just the concept is the exact same concept. If I walk into a bank, I'm like, dudes, I have an interest-bearing savings account at this account, like a bank account. Like I have money in there with you guys, and we have this arrangement where, like, for the privilege of holding on to my money, you're giving me interest every day, right? Like you give me 1.25%, whatever. Like you're actually adding money to my money every day. Thank you very much. So, bank guys, I'm here to say, how much money's in my account? I ask, like, what is X at this moment in T? What's the value of my money right now at this moment? I say to them, and they say, oh, fair question, Yaverbaum. Well, as you said, it's an interest-bearing account. So we can get you that answer. But of course, it depends on how much interest was put in your account today. Like every day we put in interest. So if you want to know how much is there, we got to know how much interest we put in. Because even if you deposited 100 yesterday dollars, if we put in $1 last night of interest, then the answer would be 101 today, right? So I say, how much money is in my account? And please bear with me. And again, I know you know where this is going, but I say, how much money is in my account? And they say, depends on how much interest we just added. And I say, good. Well, how much interest do you just add? And of course they say, well, that depends on how much money's in your account, right? That don't, like, I want you to dwell on that. Don't skip that part. That part that might have even confused you when you first ever thought about interest. Like that's the thing we're trying to unpack here. That's called feedback. When the rate of change of effect doesn't depend on cause, but depends on effect. When the dependent variable is on the right side, that is the issue of feedback. And what I want to say now is, look, everyone, look at exponential functions, trigonometric functions, and complex functions. Let's look at them all. Like, look, trigonometric functions, like why did it work in the first place? Sine. If your first original function, if your function is like f to the 0 equals sine of x, then you take one derivative. So like f prime, right? You get cosine of x. You take another derivative, f double prime, you get negative sine of x. Another, you get f triple prime equals negative cosine of x. Now take a fourth one, take a fourth derivative, clock your derivative, and you'll get back to sine of x, right? In other words, sine of x will cycle back to itself given 4 steps. If you take 4 derivatives, you're definitely going to get right back to where you started. Similarly over here, I should have made clear, with e to the x, since you get the same thing every time, for sure, after 4 steps, you'll be back. Like you don't even need 4 steps with e to the x. You just need 1 step. You get back to itself. But since that happens every step, if you think about it, you could hook like e to the x and sine of x can be hooked up together in steps of 4. And every 4 steps, they'll end up back where they started, right? Derivative of e to the x is e to the x. Derivative of that is e to the x. Derivative of that is e to the x. Derivative of that is e to the x. And now look at I, if you didn't already, at the bottom of the page. I to the 0, like anything to 0 is 1. I to the 1 is I, that's square root of negative 1. I to the 2, I squared, right? I mean, this is like taking, and every time you take a derivative with chain rule, you're multiplying, right? So this is the same concept. I squared, you get negative 1. I cubed, well, that means I times I squared. So that means I times negative 1. So that's negative I, right? And then I to the 4th, well, that's I times I cubed, or it's I squared times I squared. It's negative 1 times negative 1. It's 1. So after 4 steps, you get back also to the original. In other words, something about complex functions, exponential functions, and trigonometric functions, all of them, as long as you're at least willing to wait for 4 steps, they all cycle and they all feedback. They all feedback, and they feedback together. If you put them together properly in steps of 4, they take care of the negative sign. The summary of this right now is well, okay. All right, I'll just read this out loud. I mean, so this is like a observation, remark, comment. So to summarize, like where we are so far, like so any differential equation you ever see ever, in because there's going to be more even in this class, but in physics, in chemistry, in PChem, if you ever see a differential equation, definitely something is feedbacking on something. It might be an abstract variable that you're not familiar. It might be electric field or something, but whatever it is that you're measuring, if it's a differential equation, the rate of change, some kind of rate of change of that measurement is depending on the measurement itself, which means there is this feedbacking thing, like whether whatever analogy works best for you, whatever example works best, whether it's acceleration, position, acceleration, or interest, principle, interest, or radioactive decay, or two mirrors looking at each other. If it's a differential equation, it's a feedback situation. And therefore, any solution that works to any differential equation, certainly ours that we have right here, but the only math that will ever solve, the only kind of functions that will ever solve a differential equation are what we call transcendental functions. These kinds of functions, these infinitely differentiable functions like sine, cosine, e to the, like, as opposed to what? As opposed to algebraic functions, power functions, as opposed to power functions. All those are finitely differentiable. Anything that describes a feedback phenomenon will have infinite derivatives. It will have this self-referential quality. And the best thing, and why this is partly useful, is like, this means in all of life, in all of nature, there's really only 2 types of functions. Like everything that happens in nature, everything that happens in space, time, matter, life, energy, like whether it's biology, chemistry, physics, if something's happening in nature and it's happening in time, then there's some kind of function to describe it. Like, or at least if scientists are dealing with measurements and stuff, then they'll describe it with some kind of function. And what we're really saying here, if you're paying attention, if you're with this, is there's only two types of functions in the world. There's finitely differentiable functions and there's infinitely differentiable functions. I almost want to write this down, but I'm not going to. Like, literally, there's functions that you can differentiate in a finite number of steps, or functions that you cannot. Things like sine and cosine and e, you cannot differentiate in a finite number of steps. Those are the ones that describe something that builds on itself or builds off itself. Like any of those functions ultimately is what we use to describe feedback, like things getting, and that's what we really mean by exponential. We like when we say exponential, we don't just mean big or fast, like even though the news uses it that way. Exponential means it feeds on itself. It means that the rate of growth depends on the growth, right? Like, so that it either gets worse and worse, like at rapid rate, or it gets better and better, but right, not just better, but better and better, right? It's like one of those things where like, I don't know, like those things, like interest-bearing, radioactive decay, population growth, etc. So there's only two types of functions in the world: those that feed on themselves forever like that, or those that don't. Those that are finitely differentiable, those that, like whether they're parabolas or cubics or whatever, those that if you take enough derivatives, if you differentiate enough number of times, if you look at rate of change closely enough, then those eventually always pile down to linear functions, constant slope functions. I'm saying for anybody who's paying attention in life, there's only two ways things can happen in nature. Either they're building on each other, on themselves, like positively feedbacking on themselves, or negatively, or they're just steady. But there's no other thing, really. There's no other kind of change. There's either feedback change or not change, right? And I think that has all kinds of implications in science, but I'll leave that for the moment. But that's okay. And so therefore, anything you can describe with a cosine, you can describe with an exponential, as long as you stick in a complex number, or vice versa. Like, I guess to summarize all of this, this is called Euler's equivalence. All right, just write this to summarize mathematically. I'm saying it is all time treated. I'm sorry. I mean, believe it or not, so I am saying cosines, i's, and exponentials all seem totally different, but they're all linked together by feedback. They're literally linked together in the sense that from here on in your whole life, and i's are used as much in physics. Imaginary numbers are used as much in physics as angles are. Circuits, well, we'll get to it, but anything that you can describe with an exponential function, you can describe with a complex trigonometric function, or vice versa. This whole page right here, this is side note, I wouldn't test you on this page. I would not. But just so that there's a takeaway of everything we're doing, I just want you to see, we are saying that what links together the seemingly completely different worlds of exponentials, trigonometrics, and complex, what links them all together is feedback. And this whole page is called, just if you want to know or ever look it up, this is why people know that e to the pi I equals -1, if you've ever heard of that, or this is how we know how to calculate pi and stuff from this business. But this is called Euler's equivalence. And this is all coming out of part I and J of the homework. Okay, which I'll go back to the homework now because I know this is getting a little abstract, but that's where it's at. All right, all right. I think that's the end of those. I think that brings us to part 2 of the homework, right? Oh, and there's 5 minutes. And that's perfect because part 2 is just kind of exercises. I'll show you my answers right now. There doesn't tend to be as much questions about the next part of the homework. So I'm going back. I believe that brings us to the end of part J, subpart J of part 1 of the homework. So I believe then what comes, is part 2. So here's part 2 of the homework. We have like 4 minutes. I'm just going to show you what I think the answers are. If there's any questions. And I'll say just quickly too, I'm just going to, again, I also, I wrote down the answers here in these class notes. So even if I don't talk through all of this, when I post the class notes, the lecture notes, like in 5 minutes, like it'll all be here. So any answers you want to check, And again, with the homework, which I think you guys are doing great, but I don't always mark right or wrong. Like sometimes I'll say okay, or we'll discuss. So just because I check something doesn't, if I say good, doesn't totally always mean that it's the right answer. But anyway, here are the answers. The real purpose of A and B is it's sort of asking the same questions over and over with two functions that differ by virtue of a phase constant. So it's really trying to show you the kind of impact of a phase constant on this cosine function. So this is now part 2. This is totally about cosines. This has nothing to do with complex numbers or exponential numbers or anything like that. But with 3 minutes left, I believe, I hope you know where I am. So part 2A, I believe the answer is 4. I mean, I'm just plugging in. It asked when t is 0, what's x? So the cosine of 0 is 1. So I believe x is 4. So that's basically says what that's really saying is that phi, the phase constant here, is 0, right? So we're assuming we started the clock when this thing was at the amplitude position of 4, right? Because there's no phase constant. That's what this is saying. Then part 2, now it's asking what are the times that you might find the thing at equilibrium, at x equals 0. So when are we going to find this thing at equilibrium? Well, many times, right? It's an oscillator going on forever, but it's asking for the first 2 times. So I just solve for the 2 lowest values. And what I get is right here, I get at t equals 1/2 second and 3/2 seconds, right? And then from there on, it'll be a pattern, 5/2, 7/2, presumably. But right, it'll take a 1/2 second for this thing to be at equilibrium because I didn't start measuring at equilibrium. I started when it was at the amplitude position of 4, right? The way the equation's set up. I mean, so so that's the answer to that one. I'm looking at the time. 3 minutes. I'm just going to keep going. Please put questions in or answers and again, this is homework 2, part 2. And again, if you didn't do it, you still can do it, blah, blah, blah. All right, next page. Then part 3, same thing. It's asking now, at what times will this thing be at the amplitude position? Well, I mean, this is the math, but I mean, my answer to me makes sense. Well, the first time it will be at the amplitude position is right at the beginning, because that's why it's the amplitude position. And this thing did not start with a phase shift or a phase delay or anything. It started with a phi. This all assumes that phi was 0, and it was 0 because because it doesn't say plus phi or anything there. Phi is what we call it in this class. Delta is what some people call it on the internet. So if you got your homework 3, well, I'll get back to that. But if there's a lot of deltas in your homework 3, please try to make sure you understand how those deltas could have been phis from this class and that they're equal to 0. So make sure whatever you got from the internet for homework 3, if you did homework 3, if you have a lot of deltas and you got something from the internet, just make sure you see how it syncs up with class. Hopefully the internet helped you understand class better. Don't use it as a substitute. You know what I'm saying? And people are coming in for the next class. All right, so very quick. So I think these are the answers to this one, 0 and 2. Those are moments in time when the oscillator will be at the amplitude position. Yeah, and then 4, it's asking what about on the other side, so it makes sense. It'll be 1 and 3 seconds, which just all has to do with knowing inverse trigonometric functions, arc, cosine. So I get that answer. We're going to stop in a second. Then 5, I get this. I mean, I'm going to post these notes and we're going to wrap up here. But the key really, if you're trying to get anything out of these exercises besides exercises with the cosine, just the feel for the cosine, just see how the answers differ then. All the above results for 2A, just contrast them with the results you get for the corresponding questions in 2B. That's showing you what the phase constant phi is all about. It just means that we started our time for the next answers, it's the same function, but A, it's wiggling twice as fast, but B, also we started our clock a quarter of a cycle in, right? That's what we're looking at now, and I'm going to shut up right now. But this pi over 2 mean, which we call phi, we're saying phi equals pi over 2. On the internet, they would say delta, but we would say phi equals pi over 2. And what does that really mean? It means we started our clock a quarter cycle into the motion. Why a quarter cycle? Because 2 pi radians makes a full cycle. So pi over 2 radians is a quarter cycle. And what does that mean in English? It means we didn't start our clock when the mass was at the amplitude position. We waited until it got to equilibrium. Then we started our clock. And that's why it's at the equilibrium right at t equals 0 because of that phase constant. Now I'm going to stop right there. The rest of the answers are in the sheet. Thank you very much for being so. I am going to say goodbye though. And I'm going to wait till there's questions. So I'm good, but please say goodbye. a loser that way. Say goodbye and we're good. Or stay if you have a quick question. But goodbye. Thank you, Amanda. Thank you, Melissa.
Have a nice day.
Have a nice day, Pravjot. Thank you. Yeah. Thank you.
See you Wednesday, Professor.
See you Wednesday, Isabella. Awesome.
Thank you, Professor.
Thank you, Billy. Thank you, Viola. Great. Thank you. Bye. Thank you, Lydia. Great. Thank you. Awesome. Okay. Awesome. Okay. And Farina, you're okay? Or you're good? You're good. Okay. Bye, Farina. Bye, everybody. Good night, Moon.